Hi everyone, here is the video lecture for production. This is lecture 4B. We're going to continue on here, and the first thing that we want to talk about for us is that we want to understand a little bit more about elasticity. So we have output elasticity of a variable input, and so we've defined this output elasticity of labor to be the percentage change in quantity given a percentage change in labor. And mathematically, what that ends up being for us is then the first derivative of our production function with respect to labor multiplied by L over Q. If we were to simplify this, we get then marginal product times the inverse of the average product. And so we have this ratio that's developing of marginal product of labor to the average product of labor. So then how can we use this in an example? So we're going to take our Cobb-Douglas production function, and essentially we're going to look at how to take our first derivative, find our marginal product, and then look at the relationship to average product. So we have to make some assumptions first. That is that alpha and beta are going to be positive, and they're going to be between 0 and 1. That A is going to be a positive constant. And so out of this, now we're able to show how the law of diminishing marginal product exists. We're also essentially able to show what is the proportional change in output resulting from a proportional change in labor input. So if you're following along, we're now going to actually take this first derivative with respect to L. And so we get beta times AK to the alpha, L to the beta minus 1. And as we simplify this, we can substitute back into our equation Q, so that we have beta times Q divided by L, which we know to be greater than 0. We know this to be true because we defined beta to be positive in between 0 and 1, and we know that Q and L make economic sense to us to be positive. It makes no economic sense to have a negative labor input, and it makes no economic sense to have negative output. So let's now take our second derivative. Our second derivative then is going to be negative. And once we've done that, we're able to determine a little bit about this law of diminishing marginal returns. We understand that we have this diminishing output. So we have, we essentially, if we were to graph this relationship in terms of output and input, for us, we essentially would see something like this. The first derivative is positive, where our second derivative is negative. And so we would get this concave, essentially, assumption. So now, how can we take this forward? How can we use what we've just defined here in terms of marginal product with our elasticity measurement? And so we know the formula for that, and so we're going to use that very nicely here. And so we're going to input our marginal product, which is beta Q divided by L, multiply that by L over Q, and then we simplify just to get beta. So what does this tell us? It tells us that the exponent in the Cobb-Douglas production function is actually that output elasticity. So we're now able to glean a few different things from these exponents. One is we can look right away at returns to scales. We can now use them to determine the elasticity. And now we can use the marginal product to help us in both of those capacities. So as we now switch gears a little bit, we want to talk about the relationship between our production functions. And so we're going to be looking at a figure that relates total productivity to average productivity to marginal productivity. And so what we want to do is understand the derivatives of total product and what that's telling us. So again, recall that this first panel will be essentially our total product of labor, whereas then our second panel will be then our marginal and average products of labor. So how could we construct essentially this bottom panel from this top panel? And so for us, we can start with looking at a production function that has increasing returns, then diminishing marginal returns, and then negative marginal returns. So then how can we use that information to construct marginal product? Well, again, knowing that marginal product is the first derivative of our total product function, Well, if we know that our first derivative must be positive, right, because the slope of total product of labor is essentially positive here. We also know that the slope is increasing. So it's increasing, so we now have this function until we reach some inflection point. Right? This inflection point is important for us because it tells us exactly when we are changing, we're increasing at an increasing rate to now increasing at a decreasing rate. So we're increasing, now this will tell us, give us our maximum. So now we have this going down, but we need to know how far marginal product will fall. So we want to look to the maximum of total product. And we know then that after this maximum point here, marginal product is essentially has to be negative. So that's how we know the intersection occurs at this point as well. So now we've constructed marginal product of labor. We now can try and create this average product of labor. And we know a few things as well. We know that as marginal product is rising, right, we should have average product rising as well. So how do we determine what the average product of labor is? Well, in our top panel, we essentially know that Q divided by L is equal to that average product of labor. So if we were to take each quantity at L, and then, so this is Q at L1, this is L1. So now if we take this Q at L1 and divide by L1, that gives us our average product at L1. And so we can take this, and it's a straight line through the origin. And we can continue to do this to see that average product is rising. So if I keep taking these straight lines through the origin, find that average product is rising at every point until it doesn't, until it stops, until it starts falling right around this point here. So what does that tell us? It tells us then that average product essentially is maximized. So when we go do that, we realize that the intersection of marginal product and average product has to occur at essentially the maximum of average product. So we know that this to be true as well. And so why do we know that this intersection occurs here? Well, we know that as essentially as marginal product is rising and is greater than average product, it's pulling up that average product. And essentially when we have the marginal product below average product, we think that it's pulling down average product. So when they're equal to each other, it must be that average product is not changing. And mathematically, when we see no change, we would say that derivative is 0, which means we've reached essentially a maximum for ourselves. So now we're going to take, after we've constructed this, we're going to take each part of these in stages. So stage 1 of production for us is this specific region up until average product is reached its maximum. So this is the region where average product is essentially greater than marginal product is greater than average product. And again, it's being thought up as pulling up production. Labor is overutilized in this region where capital is underutilized. Essentially, why do we know this? Because labor is very productive at this point. So we want to be using in our production projects as much labor as possible. So if we believe that wages and prices remain constant, then additions to labor make the average labor more productive. We know that this to be true, which then in turn makes average profit per worker rise as well. So if we're getting on average more output as we add additional workers, and if prices remain constant, that means profits must be rising. We say that firms wouldn't operate here knowing this, and that's because they realize that they want to keep pushing that marginal product and average product. They want to keep adding labor and adding labor. And that moves us into stage 2 then. So in stage 2, if we go back to our drawing, stage 2 then is where we reach this essentially the average product maximum all the way through to essentially the marginal product becoming negative. Here, it must be that marginal product is positive but it has to be less than average product. And any labor additions essentially are pulling down average product. Average revenue then, if we think in the same context, average revenue and profit per worker would also be falling. Because if workers are less productive and we pay them the same amount, then essentially we're going to be getting less and less profits, which then moves us into this third stage of production. So this third stage of production is an important one. This is the stage where marginal product is negative. So again, similar to stage one, we won't be producing here. We understand here then that average profits will be assumed to be falling with any increases in labor usage. Here labor is underutilized and capital is overutilized in this instance. So with these conclusions then, we know that the amount of capital and labor will be within the boundaries of stage two. This exact amounts are not really known to us right now though. So how can we begin to determine what the exact amounts are that we want? So we can start with looking at something called an isoquant. So by definition, isoquants are essentially the combination of capital and labor or any other n-dimensional combination of inputs which are necessary to produce a given level of output. If our inputs are divisible, then this means that we have an infinite amount of possibilities in constructing some level of output. So this is a problem for us because we want to know exactly how much capital and labor to use. So in this instance, what we can do is create an isoquant to tell us the substitutability of capital and labor. We're now able to visually inspect what the substitution is. The very first thing that we need to define then or understand is that within this, what we want is to have essentially a fixed level of output. This is an important decision for us, and we're going to mark that in our production function as well. So how would we observe this isoquant? So we start with creating a fixed level of output here for ourselves. And then what we're going to do is essentially solve for K, right, or solve for capital in terms of then L and Q. So now this fixed level of quantity shows up in, or will show up in, a new equation for K. So once we've done that, once we've set up this equation, what we now can do is look at the slope of this equation. And in order to do that, we're going to take the first derivative with respect to labor, because this will tell us how does capital change as we change labor. And so this is essentially what we define to be the marginal rate of technical substitution. We are going to believe that this marginal rate of technical substitution is less than 0, and that's important for us. And that intuitively makes sense, that if we eliminate capital in our production process, we have to substitute that with increasing amounts of labor. So what is the relationship then? The slope is this MRTS. How can we see this a little bit better? Well, it essentially tells us that we get this outcome, that the MRTS is equal to the negative MPL over the MPK. And so why did we know that this is true? So if we think of the MRTS, essentially as changes in capital over changes in labor, and we say that that's equal to this negative MPL over MPK. Let's rearrange this so that we get the change in capital, NPK, is equal to the negative MPL change in L. What essentially this tells us is that given this now says we're not only relying upon some change in capital and some change in labor. What it says is that the proportionate change of capital has to be equal to the proportionate change in labor. So proportionately, we must be the same. So that when we look at this isoquant, in order to move from A to B in this instance, in order to move from A to B for us, we first have to move from A to C, and then we move from C to B, right? And so what this says is that we're reducing the amount of capital by this amount, how productive it was times the change. And we have to add in then this proportionate change in labor. So what other characteristics of the isoquant can we analyze here? The first being is that these come out of a very mathematically complicated concept to define, and that is convexity. Now, convexity for us in this instance is going to be that the marginal rate of technical substitution is less than 0, and the second derivative has to be positive. So this is our necessary and sufficient conditions to know that our isoquant is convex. So we find, though, that inputs are not perfectly substitutable here. What we have, because of this convex nature, that there's some sort of decreasing degree of substitutability. If they were substitutable perfectly, then we would have a linear isoquant. Okay? So the linear isoquant might be for something like natural gas and electricity. So what we get is some negative value where our second derivative would have to be then 0. So if we think about this a little bit, that would mean for us that our first derivative, if our first derivative is less than 0 and our second derivative is equal to 0, the only way that this occurs is if the MRTS is a constant value. So for example, if our MRTS is equal to 5, then the derivative of our MRTS is equal to 0. And so that would mean, sorry, negative 5 we'll say. So then that would mean we have a linear isoquant, something like that. We can now talk a little bit about and switch gears into kind of different shaped isoquants. So we want to continue looking at different isoquants here, and so the next one that we want to look at is what we call our fixed input isoquants. So the actual isoquant themselves will have a very specific L shape for us. So we want to think of this as that we have a fixed amount of inputs that we can use. So if we want to buy a pair of shoes, we can do so by buying the inputs of a left shoe and the right shoe. We can also think of this as maybe a baking process or a chemical process, but we have some proportionate amount of fixed inputs. And so right away we believe that these isoquants will look something like this. So if this is our labor and this is our capital. So this is an isoquant for some Q sub naught. So how do we continue looking at this process of isoquants then? Well, really our production function for fixed inputs, or we could also call it a Leontief production function, is basically based on the minimal proportions of the process. So in this instance, in our example, if we were to use capital and labor in 1-for-1 inputs, then what we're required to do is essentially we can only produce at the minimum amount of labor or the minimum amount of capital that we have. So this minimum doesn't mean to minimize in any way when we draw it here. So when we say that our output Q is equal to the minimum of K and L, it actually means the minimum amount of capital and labor that we have. So if we look at, if we're making shoes, so if we have a right shoe and a left shoe, and so we can have inputs of left shoes of 1, 2, 3, and 4, and inputs of right shoes of 1, 2, 3, and 4. So now for us, if we want to make with an isoquant of one pair, right? So Q is going to be fixed, is going to be one pair of shoes. Well then, what does our isoquant look like? Well, we know that if we were to have just one left shoe, we could have as many right shoes as we could have, possibly. essentially. We could have as many right shoes as possible. We can still only make one pair of shoes. And if we had one red shoe or one right shoe, and we essentially had as many left shoes as possible, we still can only make one pair of shoes. So this intersection of these two lines gives us the isoquant that we want. So again, it's the minimum amount that we have. And so this is important because this unique L shape is not differentiable. We can't differentiate this. We can't take essentially the derivative, and it would not mean anything for us. So if I were to marginally add an additional shoe, right, we still could only make one pair, right? The change in output is zero, is nothing. And so this is, I think, a very important point to make here, is that the marginal product essentially is zero in this instance, or undefined if we go the other way. So what is another example of this? So suppose that for every unit of production, we were required to use 2 units of capital to every 3 units of labor. So to illustrate this production function, essentially you would need to know how much of our inputs you had, and you need to take the minimum amount to know how many goods that you can make. But the production function itself would be written in this way, that Q is equal to the minimum in proportion, so 2K for every 3L. You could also write it in this way, which is also maintaining that proportion, that for every 2/3 capital, you need 1/3 labor, or I'm sorry, you need 1 labor. Or again, you could write it in this way, that for every unit of capital, you need 3/2 labor. So you can write production in this way. So picture-wise, what does this mean? So we have essentially our capital and labor, and we know then essentially at 2 and 3, we have our production function. And this is our isoquant for Q is equal to 1. And so what we know to be true, though, is that any time we scale up our production, we would need to have 6 units of labor and 4 units of capital. So again, this would be for our isoquant of Q is equal to 2. So what we end up having is we realize that we find this ray through the origin. Now this ray through the origin says something very specific, and that's the relationship that we have, that 2K is equal to 3L. So that K is equal to 3/2 L. So the slope of this ray essentially tells us that our isoquant must be there on this ray. And I think that's important as you scale up or scale down the units of production. So we want to switch gears here, and we did this example in class, but we want to say derive an equation for an isoquant with K in terms of L. So basically, we want to take this and say that Q sub naught is now going to be some fixed input, some fixed amount. And now, in order for us to solve for this, we essentially just want to solve for K. So we'll take Q sub naught, and then we have A to the -1, L to the negative beta is equal to K alpha. So now what I'll do is I'll take all of this to the left-hand side. I'll raise it to the 1 over alpha. So I have K alone. So now what I could do is, this is now my derived equation for the isoquant. This is isoquant when Q is equal to Q sub naught. So now we want to demonstrate it's convex. And so for that to be true, we know that the MRTS has to be less than 0, and that we know that the derivative of MRTS has to be greater than 0. This is our convexity property. So let's start doing that. So let's take the derivative of K with respect to L. So dk dl then tells us that we have alpha Q sub naught, keep the inside the same here, then we'll have 1 over alpha minus 1 times the derivative of the inside, and the derivative of the inside with respect to L is negative beta q sub naught a to the minus 1 L to the minus beta minus 1. So now how do we know that this is less than 0? Because we know that alpha and beta essentially have to be between 0 and 1. That's true. We also make the economic leap that A, L, K, and Q are greater than 0. And I don't think that's a big leap to make. We know that A will be a positive constant. We think that output Q will be a positive constant. We also think that we have positive amounts of L and K. And if that's true, then the only negative that we find is here, right, in our equation. So we know then that this first derivative, dk dl, has to be less than 0. So now we can now take our second derivative, essentially. So in order to take our second derivative, let's clean this up a bit so that we have negative 1 over alpha beta q sub naught a sub naught, and then we have L to the beta plus 1, and we have q sub naught a to the minus 1 L to the negative beta 1 over alpha minus 1. Okay, so we could distribute this out, and that would be fine to do. Or we could just take the product rule essentially here. Either way, when we do this, we're going to essentially find our solution. So let's click over to the solutions here, and that we get now, we essentially get that our second derivative is going to be positive. And so how do we know that? Again, it's specifically that we know that we have our negative sign here. We know that beta and alpha are going to be positive constants that are going to be less than 1 but greater than 0. And the same thing here is that we realize that Q is going to be positive, A and L are also going to be positive. So when we solve for this, we realize that this will be a positive value because we now have this second positive number as well. So we know that this will be negative, this will be positive, negative, and so overall it becomes a positive value. So when you're trying to determine the shape of these isoquants, you want to rely on the first and second derivative in order to do that. So the next little bit that we talked about is this long-run production function. And this, again, was very general, and I just wanted to introduce this. And really here what we want to say is that our constant returns to scale has another mathematical property to it, and that's called homogeneity. And so a constant returns to scale production function is thought to be homogeneous of degree 1. And essentially that means that we can scale our inputs and we'll also scale whatever output of our function to be by the same amount. And this will work with any function that we talk about that exhibits this property. We can look at increasing returns to scale then as a function that has a homogeneous of degree that's greater than 1, and a decreasing returns to scale production function is thought to be homogeneous degree less than 1. So again, we're going to use this later on in class, but I want to make sure that we are properly just noting what it is right now. And so we had some practice problems that I had you guys do in class that I wanted you guys to prepare for, that we didn't really go over much, but these would be good for us. And I would think with these production functions, not only could you determine is it constant returns to scale decreasing or increasing, but now with these you could also practice your marginal rate of technical substitution calculation, forming your isoquants, and determining the shape of the isoquants as well. So I would urge you to do that. And the last thing that we did in class was talking about estimating the production function. And so in Sakai, we have a folder which houses another PowerPoint and the data that we used in order to go through the estimation techniques. But for the quiz and for the test coming up, none of this information is relevant. This is really for you to understand how we can use this information in the real world. So if you were at a firm and you were trying to understand your relationship between capital and labor, you have some basic knowledge in order to do that. And really, this is where we ended our lecture over 4B.